Okay, so I apologize for failing to send out a reminder earlier this week about this meeting with the agenda topic, but the agenda today is to talk about the decentralized coordination for federated lingua franca. And so I'm going to lead that discussion, but feel free to interrupt with comments or questions at any point. Um, so let me share my screen. Need to share the right desktop. Okay, here we go. All right, so I'm as you all know, I'm primarily interested in cyber physical systems. So I'm interested in machines that when computers that interact with the physical world. Um, but I'm going to use a running example here that is uh, it is technically a cyber physical system, although people don't usually think of it. Think of a very simple banking application where you have a distributed system where you've got user interfaces, which in this case are represented by these WebSocket servers. So think, though, like an ATM machine where you can deposit money or withdraw money. And that's kind of where the cyber physical aspect of this comes into play. You know, if you deposit cash, it gets swallowed by the machine. If the machine dispenses cash, that's an actuation in the physical world that is very difficult to reverse later, and that's an important feature of cyber physical interactions, is that they're usually irreversible, or at least there are actions that you take in the physical world that are irreversible. And in this particular application, we're maintaining a distributed database so that we have account managers that are potentially scattered around the world. And you can think of this as the world's smallest database. So in this particular case, this account manager. The whole reactor is shown right here. It receives deposit or withdrawal notifications from ATMs around the world, okay, or bank branches around the world. And it processes them to maintain a local copy of the balance. So there's a state variable maintaining the balance. And in this particular implementation, all it does is when it receives an input in one, it adds that input to its local copy of the balance and reports that balance. And similarly, when it receives an input in two, it adds that number to the balance, okay? And then it just produces the resulting balance on the output and then reports that back to the ATM machine. So if I compile this program, as usual, let me point out that this is a federated program. So that's indicated by this federated keyword here, which means that each of these top level reactors will code generate into a separate program. Okay. And the coordination between these programs is decentralized, which is the more experimental part of the federated execution in lingua franca. And it's a part that we're frankly learning a lot about. And I'm kind of coming to the conclusion that it's a lot more powerful than we initially realized. Okay, and so that's part of what I'm going to try to show you today. So the other thing to note about this particular application that I've started with is that the connections between the federates are all physical connections, as indicated by these little squiggly lines. So those are constructed using this squiggly connector, which means that that timestamps are not conveyed. And consequently, there's no semantics to the ordering of events when they arrive at one of these account managers. They're just going to arrive in non-deterministic order that will be dependent on network latencies and so forth. Okay. So this is a principle, in fact, that or a strategy rather, for distributed execution that is really very old. Carl Hewitt described this strategy way back in 1977. And in fact, this style of coordination is often called Hewitt actors, where messages arrive in non-deterministic order and are processed by message handlers in non-deterministic order. Gulaga subsequently developed quite an elaborate formalism around this. And so these are often called Hewitt-Aga actors to give Gulaga, who was a PhD student of Carl Hewitt's, credit for this. And so this is a classic paper from 1990 that talks about this particular model of computation. Okay, so that's so the essential point is that you can essentially implement Hewitt actors in lingua franca with decentralized coordination using physical connections everywhere. So when I compile this program, I get, let's look at it, I get 4 distinct executables because there's 4 top-level reactors. So these will be deposited in a directory that is named after the program, which is accounts 1. And there's a bin directory here. And you can see that there's 4 executable programs that were generated at 8:14 in the morning on November 20th, which is 2 minutes ago or 3 minutes ago. Okay. And in addition, for my convenience, the code generator generates a shell script that is named after the program and inserted into a bin directory. This is what the shell script looks like. It's simply a bash script. And this shell script launches these 4 programs. And in this case, I'm just launching them all on my current machine. But actually, you can map them to other machines around the world, and you can also put them in Docker containers and so forth. So, all right. So if I run this script, it'll start up the 4 programs, and 2 of these programs are running web servers, and those web servers are giving me a hint to point my browser to a certain location. So let me point my browser to localhost port 8080. So now I've connected to one of the web servers. And over here, I can, in a different window, point my browser to localhost on port 8081. And now I've got two of the world's ugliest ATM machines. Okay, I'm not a user interface designer, so I apologize for the very ugly user interface, but on these ATM machines, I can, for example, deposit $100 here, and I get a reported balance of 100, and so does the remote one get a reported balance of 100, okay? I can deposit another 200 over here. These could be some, scattered around the world. So think of this ATM machine being in London and this one being in Singapore, okay? Now I've got a balance of $300 here, but now there's a bit of a problem with the implementation that I have here because it allows me to withdraw $1,000, and sure enough, the balance goes to negative 700. Okay, now, well, why is that? Well, if you look at the program, okay, what the account manager is doing is simply adding the values that are deposited and withdrawn to the balance. Now, there's a reason for this. In fact, this strategy is quite popular among distributed systems designers. It uses essentially a merge operation to merge updates to the shared data that is sometimes called ACID 2.0. And that terminology comes from this paper by Pat Helen and David Campbell from 2009. And these guys are distributed systems experts. And ACID in this case stands for associative, commutative, idempotent, and distributed. Okay, so the distributed part of it is the easiest. Okay, this is a distributed program. Idempotent means that if that when there's a transaction that's going to change the value of this shared variable, um, essentially it either gets applied exactly once, or if it gets applied multiple times, it doesn't have any, it has the same effect as being applied exactly once. Okay. So you could build a distributed implementation that actually repeatedly sends these transactions, gives them a unique ID, and then makes sure that they only get applied once. But in the case of Lingua Franca, the connections between these reactors use TCP, and consequently, they get reliable in-order delivery, which is a key part of the abstraction that TCP provides. And consequently, messages are in fact received exactly once and applied exactly once. So we get idempotence for free. Commutative and associative is more subtle. Okay. So the particular operation here of just adding to the balance is commutative and associative. You can apply these additions in arbitrary order, and you can group them arbitrarily. And as long as everybody eventually gets the same messages, the two account managers will agree on the balance. Okay, so as a consequence, you get a eventual consistency. Eventually, if transactions stop occurring, the two account managers will agree on the value of this shared variable. Okay, this same principle appeared under a different name, which is conflict-free replicated data types, or CRDTs, which have kind of become all the rage in distributed systems. And people try to design systems using these sorts of data types that have these properties of associative, commutative, and idempotent operations. Okay, so there's good reasons why people might want to do this, but there is a problem with this, which is that if I were able to, well, I mean, a key problem is for this particular application, there's no way to prevent an arbitrarily decreasing bank balance. Okay, I can withdraw another $1,000 over here, and my bank balance is going to keep going down. And if I try to guard against overdrafts, my operations will no longer satisfy this acid property. They'll no longer be commutative. Okay, so let's look at an implementation that in fact does some overdraft protection. So this is a second version of this program. Okay, it's still using physical connections, so it's still Hewitt actors effectively. But this account manager is now a bit more complicated. So it's imported from a library file. So let's have a look at it. Okay, the account manager, again, is just a single reaction, but let's just look at the documentation for it. So it says it accepts deposits or withdrawals on two inputs and maintains a bank balance and prevents overdraft. So if the deposits and or withdrawals at any time result in a negative bank balance, then one or more of the transactions will be rejected and a penalty will be imposed. Okay. In particular, if one input is a withdrawal and the other is a deposit, then the withdrawal will be rejected. If both inputs are withdrawals, and then if in one alone doesn't result in a negative balance, then the in one withdrawal will be accepted and the in two withdrawal will be rejected. So, et cetera, et cetera. We don't really, it's not really that important what exactly is the logic here. What's important about this is that this is a business decision. Okay. The bank wants to use a policy here. All right. And they want the software to implement a policy. It's not a technical decision, it's a business decision. But it results in non-commutative operations. Okay. If I run this program, let me kill the previous one. And I've already compiled all of these programs, so we don't have to watch the compiler code generate these things. So let me just start accounts 2 and go back to my ATM. And I need to reconnect these guys. Okay, so I've got these 2 ATM machines. Let me deposit $200 over here. And now I'm going to attempt to withdraw $300 here. And you see that, in fact, I didn't get my $300 and I got a penalty of $30 for attempting to withdraw too much. All right. So in this case, of course, the balance is maintained consistent in both cases. But the reason for that is that with this user interface, I can't simultaneously perform withdrawals, right? I just can't do that quickly enough. But if this was an ATM in Singapore and this was an ATM in London, and they both tried to withdraw, say, the $200, it's quite possible that the system would, in fact, hand out $200 to each of those two, resulting in a bank balance that will be, in fact, in overdraft. Okay, so we can create a test case that tries to do that. Okay, so this is what my version accounts 3 does: is it replaces the ATM with a finite periodic source. Okay, which in this case is a simple reactor, also drawn from, where is it? Right here. So this simply starts at some time offset and generates periodic outputs for a given number of repetitions. So in particular, what the test case does here is, with one of the periodic sources, every 1 second it deposits $100, and every 2 seconds it withdraws $200. Okay, so if all the timing is controlled, there would be no overdrafts. Okay, but the timing is not controlled, and consequently, you will non-deterministically get overdrafts. So if I run this program, accounts 3, we may see some overdrafts. We may not. Oh, looks like we got an overdraft. Oh, looks like we got another overdraft. Okay. Now, coincidentally, these 2 overdrafts in this particular case, let's see, one of them happened at account 1, the other one happened at account 2. So because it occurred I got exactly 2 overdrafts, and in both accounts, then the balances still maintained agreement. Okay. But in general, if I run this repeatedly, there's no assurance that these 2 will agree on the balance. If this overdraft had not occurred, then the 2 would get out of sync, and they'll stay out of sync. Okay. This is really a principle that is behind this idea of ACID 2.0 and CRDTs. And Shulu next week is going to show us, in fact, that these ACID 2.0 properties are not only sufficient to maintain eventual consistency, but they're actually necessary as well. Okay, that there is no way to guarantee eventual consistency without having this ACID 2.0 property. Okay, so that's potentially a pretty serious problem, right? Because it means that we can't implement the business logic that we want in this account manager, because it's not a commutative operation while still maintaining a distributed replication of the data. Now, of course, there's a number of solutions to that, right? One is, well, don't maintain distributed copies of the data. Okay, so have the data in one central database, just one location. But that, of course, creates a single point of failure. And it also means that if you lose connectivity to that one single point of that one single resource, you're going to lose availability. You're not going to be able to operate the ATMs, and that might not be acceptable. And again, I emphasize that, well, in this banking situation, maybe that would be a reasonable solution as long as you could provide some, ultra reliable centralized database. But in a lot of cyber physical systems, that's not going to be acceptable, right? So you can't say, well, I couldn't apply the brakes because I couldn't reach the server, all right, or something like that. If you've got coordinated vehicles that are trying to coordinate across networks, it's not going to be okay to just have a centralized single point of failure that maintains the state of the system. Okay, so we have to find a solution to this problem, right? And we want to we need operations that are not commutative, and we have to um, uh, find a solution. Okay, so let's look at a solution. So if we go to accounts for, whoops. So this again puts back the WebSocket server, and now it uses this account manager. But the only difference here from the previous iteration is that these are no longer physical connections. Okay, so what this means now is that there is a temporal semantics, and the order of the operations has a semantics. And in particular, in the web server, what happens, this is a little bit of a deep hierarchy, but at the root inside here, there's a physical action. So what this does is this assigns a timestamp to the ATM operation, deposit or withdrawal, based on the local clock. Okay, so this is going to be based on a clock in London or a clock in Singapore. It assigns a timestamp to the deposit or withdrawal, and that timestamp is semantically conveyed, and the account manager is required to process inputs in timestamp order. Okay. Now, the important thing to realize is that one of those timestamps might be assigned in London, one of them is assigned in Singapore. There is no universal clock in the sky. Well, there almost is. You could use a GPS clock, but even GPS clocks are not perfect, right? So, the actual physical ground truth of the order in which these operations occurred is actually not what is interesting here. In fact, there is no physical ground truth. If a transaction in London and a transaction in Singapore, if they're less than 30 milliseconds apart, there is no well-defined ordering as a fundamental physical principle. Okay, the order in which those transactions occur will depend on the observer. So this isn't about assigning a ground truth. This is about assigning a semantics. Okay, the timestamps, once they're assigned, are just numbers. And they're numbers in a totally ordered set. And consequently, the order of those numbers is well defined. And consequently, this account manager and this account manager will agree on the order of the numbers. And consequently, if they're able to process the numbers in timestamp order, then they will maintain consistency, not only eventual consistency, but they will actually maintain a stronger form of consistency, which is that at any given timestamp, they will agree on what the balance is for the system. Okay, so that does not depend on this operation being commutative, associative, or idempotent, but it doesn't really circumvent this necessary and sufficient condition. What it does is it shifts the responsibility for ensuring this ACID property to the infrastructure instead of to the application. Okay, it's the infrastructure that is guaranteeing that effectively the operations are in fact ACID, and the programmer doesn't need to worry about it. But that isn't actually quite true. Okay, so in particular, let's go ahead and run this this program. So And we can have a look. Let me reconnect the ATMs to it. You can see that this was disconnected because the previous program got killed. All right. This is going to work pretty well, right? I can deposit $100 here, withdraw $80 here. Okay. I can attempt to withdraw $100 here. And I got a penalty of $30 and did go into overdraft because of the penalty. Okay. But I maintained consistency. But this program isn't quite right. Why not? Somebody want to tell me? So let me just pose a question, right? So when I get a deposit from this guy or a withdrawal from this guy, it arrives at my input port. Okay. The reaction in the account manager will be triggered by an input on either input. Okay. So in this particular implementation, I'm using the decentralized coordinator. Okay. And with the decentralized coordinator, there is no intrinsic guarantee that I won't later receive an input here with a lesser timestamp. All right. So I may, in fact, receive these inputs out of timestamp order. Now, I won't see that in my application test. So I fire up these two web browsers and I can test my program up the wazoo and I won't see the error. But the reason I won't see the error is that I can't do simultaneous withdrawals, right? My user interface doesn't allow it. So I could build up a completely false sense of confidence that I've got a system that maintains consistency, but it doesn't actually. And what will happen in practice is that if you get too close to simultaneous withdrawals or deposits, okay, the account manager may see inputs out of timestamp order and it will report an error. All right. The decentralized coordinator will report what it calls a safe to process violation. And by default, it will go ahead and process the event as if there was no safe to process violation. But that's the behavior you get. And then because the order is still possibly uncontrolled, you still have the possibility of these two getting out of balance. Okay. So where they don't no longer agree on the value. Okay. So this is a problem that's again a very old problem. The problem is how do you ensure that in a distributed system that you process events in timestamp order? So one technique, which is also quite old. In fact, here's the paper from Chandy and Misra from what's the date on this? It's 1979. Okay, so in the context of distributed simulation, Chandy and Misra developed a technique that is a pretty straightforward implementation of this, okay, that will in fact guarantee messages. So let's go to accounts 5. So accounts 5 uses our decentralized coordinator to implement a naive version of Chandy and Misra. All right, how do we do that? Well, when we instantiate this account manager, each of the account managers, we set a parameter that is called safe to advance to a time value, which in this case is forever. All right. So what this actually means is that when the account manager receives a timestamped input here, it can't process it immediately. It's not safe to advance its time to the time of that timestamp. In fact, it potentially will wait forever. But with our decentralized coordinator, it doesn't actually wait forever. It simply waits until it knows that it will not receive an input here with an earlier or equal timestamp. So if we run this program, it's going to give us a pretty unsatisfactory behavior, but it's at least a step in the right direction because it will maintain um, consistency. So I reconnect to my two ATMs, and let me go ahead and deposit $100 here. Now, what happens? Nothing. Okay. I've gotten no reported balance, no acknowledgement of my deposit. I try to withdraw the $100 here. Okay. What happens? Oh, well, actually, the withdrawal has not been processed, but the deposit was processed. Okay. The withdrawal, in fact, won't be processed until I get another event from here. So if I deposit $80 over here, then the withdrawal gets processed. So my balance went to zero, but the deposit of $80 didn't get processed. Okay. So it's got to wait for inputs on each of the two inputs. So this is a naive implementation of Chandy and Misra, but Chandy and Misra obviously were not naive. So they said, okay, well, what we need to do is send null messages periodically. All right. So if I just send a zero, then I get the balance, and this guy can send a zero periodically. So each of them can send zeros periodically, and we get an actual implementation of Chandy and Misra, which is shown here in account 6. And here I have modified the server so that it still has this WebSocket server in it, but in addition, it has a wrapper around it that ensures that once per second it will send out a transaction with value 0. Okay. If you look at how this reaction is implemented, it writes to the same output that the WebSocket server writes to. It checks to see if the WebSocket server has coincidentally produced a transaction with that timestamp. And if it has, it just leaves it alone. Otherwise, or forwards it, I guess, forwards that transaction. Otherwise, it sends a null message. Okay. So this implements Chandy and Misra, and of course, that's going to give us a better behavior. So if I run this account 6, now I can, deposit $100 here, and within a second, whoops, I need to reconnect. All right. So I deposit $100 here, and within a second, it'll appear in both places. I can attempt to withdraw $200 here, and it will, within a second, apply a penalty in both places and not issue the withdrawal. Okay. So this is the Chandy and Misra technique, and it comes at a cost, of course, which is these null messages that are flowing around. And also the period of the null messages affects availability, right? So there's this 1 second lag here to get an update. So if we want to get rid of that overhead, okay, what could we do? Well, there's another technique that we can use, which is implemented in accounts 7. All right. What this one does is a little more subtle. It doesn't, in fact, wait forever for inputs. It assumes a bound on the latency. So in particular, what it does in this particular case, it assumes that if there is going to be a transaction from the other guy, that I'll hear about it within 30 milliseconds. Okay? So it makes that assumption. And this principle dates back to 2007. This paper that came from my group, Yang Zhao was a PhD student of mine, and this was her PhD thesis. And she developed this technique that we called tides, and this was published in 2007. All right. The same technique was 5 years later reinvented, apparently completely independently, by Google, some people at Google. And here's a paper describing this that was published it was actually first published in 2012. I'm not sure why this says 2013. But this principle, it forms the backbone of Google Spanner, which is possibly the world's largest database. It's the database behind Gmail. Um, and it is a distributed database. So your email is replicated in multiple data centers. Okay. And all of the email that flows in and out of this database, these transactions are timestamped using local clocks, and the semantics of the order in which the messages are dealt with is defined by those timestamps. Okay. So, so this technique just simply uses the fact that you can perhaps safely make assumptions about bounds on latency. Now, there's a couple of subtleties, right? One is that this also requires that your clocks be synchronized, okay? Because if your clocks are completely unsynchronized, then waiting 30 milliseconds according to your local physical clock is not going to provide any assurance about any timestamps you might receive from a remote server. Because if the remote server has a clock that's way out of whack, it might later in physical time send you a message that is timestamped earlier, okay? In which case your timestamps you'll see timestamps out of order. So, but of course, clocks cannot be perfectly synchronized. And so you have to, account for the possibility, or in fact, the assurance that there's going to be some clock synchronization error. And in fact, the 30 milliseconds then is not really just an assumption about latency in the network, but rather an assumption about latency and clock synchronization error together. Okay. In addition, however, because you're waiting 30 milliseconds according to your local clock and then acting, you still have a risk of actually ending up seeing a message out of order. Okay, so you have to have some kind of a recovery mechanism. In fact, you can show that this technique by itself, in fact, Shulu will kind of give us a proof of that this undermines the acid property at a very fundamental level, and you can no longer provide an ironclad guarantee of perfect synchrony. Okay. Let's see, what does the account manager do in this case? So if we look at the account manager, it doesn't provide any protection at all for out of order events. As a consequence, it's simply going to process them at the wrong timestamp, possibly out of order. If you get latencies bigger than 30 milliseconds, by default, that's the behavior you're going to get. It's the same behavior as the first model that I showed you, where there's no semantic ordering between the events. And consequently, this implementation can become inconsistent. Okay. So what can we do? All right. So there's another result that says that actually, at a very fundamental level, there's nothing we can do. This problem cannot be perfectly solved. Okay. And the proof of that is in this Cal theorem paper, which the archive version is from 2021. So this is when we first developed it. Okay. But it says that if we want to maintain availability, okay, meaning that the ATM machines will respond within 30 milliseconds. That's in fact what this program guarantees. each ATM machine will respond to a transaction from its local user interface within 30 milliseconds, regardless of what the network is doing about communication. Okay, even if the network is broken and your connection to this remote WebSocket server is gone, this will in fact reply within 30 milliseconds. So it in fact is maintaining availability. All right. And the Cal theorem says that if latency increases and you maintain availability, you have no choice but to sacrifice consistency. It's impossible to avoid. Okay. So what can we do? Well, we can throw up our hands and say, well, we can't implement a distributed banking system, but that's not going to be a very satisfactory answer. And in fact, we can do quite a bit better. So Accounts 8 provides a hybrid solution where, regenerate the diagram. Okay. This has a much more complicated account manager, and it's in fact, it's labeled account manager with recovery here. And then it has, in addition, two reactors that will, in fact, guarantee consistent balances. Okay. So these two guys are assured of maintaining consistency. But the Cal theorem tells us that that's going to cost us in availability. So we combine them with a technique, an account manager that, in fact, allows for the possibility of becoming inconsistent, okay, in order to maintain availability. So it will, in fact, always respond to inputs within 30 milliseconds, okay? But then there's this feedback from the component that is maintaining a true balance, okay, that will periodically give me information about what the actual true balance is. All right. Of course, this cannot do magic, right? If I, in fact, block on this true balance input in order to ensure that I get a true balance, I'm going to sacrifice availability. The Cal theorem tells me that. So I can't do that. And in fact, the implementation that I have here is one that simply, if and when it receives a true balance on time, it updates its version of the balance. Okay. But in addition, there's a time lag because this true balance is going to use the Chandy and Misra technique. It's not going to update the true balance without actually receiving inputs on both input ports. It uses null messages. So there's a timer here that is set to send null messages every 10 seconds. And when these null messages are received, as soon as this true balance reactor has inputs on both inputs, it can assuredly, with a guarantee of consistency, update its balance. But then it feeds it back with a logical delay. So when the account manager with recovery receives a true balance, it's actually old information. And it's going to be old by 10 seconds. So the way this account manager with recovery works is that it records inputs over a period of 10 seconds. During that time, it provides availability. So it will dispense cash, it will accept deposits, okay, during that 10 seconds. When it receives a true balance, it then sets that true balance and replays the transactions over those 10 seconds, okay, to have now a new tentative balance. And at all times, it maintains a tentative balance. And as long as the network latencies stay below 10 seconds now, the two account managers with the recovery will have only transitory inconsistencies. They're allowed to become inconsistent up to 10 seconds, okay? And in exchange for that, they're able to deliver 30 milliseconds of of availability. They can respond within 30 milliseconds because they're allowed to become inconsistent over a period of 10 seconds, which now says they can tolerate a latency of 10 seconds. And the Cal theorem now relates these three things. Okay, if your latency stays within 10 seconds, your availability is within 30 milliseconds because you've tolerated an inconsistency of 10 seconds. Okay, so this is the trade-off that you have to make in Cal theorem. And you have to also decide what is the worst case scenario. Well, the worst case scenario is your network breaks completely and you don't meet the 10 seconds. And now you have a business decision to make. Should you allow these two account managers to get out of sync for more than 10 seconds? Okay. Or do you want to, in fact, become unavailable? By the way, I mean, this is essentially the way banks work today, except that they don't use 10-second intervals. They use 24-hour intervals. Okay. Accounts get reconciled once per day, basically. And the genuine true balance gets replicated in all their distributed copies once per day. Okay, so you could make a different business decision. All right, there's a very different business decision here in accounts 9, which what it does is it accepts deposits within 30 milliseconds, but not withdrawals. So it, in fact, will not issue a withdrawal unless it has guaranteed consistent information. And as a consequence, there's no availability guarantee for withdrawals. Okay, it's possible for a withdrawal to take an unbounded amount of time if the network has failed. That's just a different business decision. And you can implement these different business decisions using this decentralized controller, which to me is kind of surprising. It makes it pretty powerful. But I'd like to show you that there's some fundamental limitations. Okay, there's still some limitations. So here I have a very simple programming pattern, which didn't show up in the previous examples for a rather subtle reason. Okay, one of the things that I didn't tell you was with these previous accounts, I didn't tell you how the server deals with inputs. Okay, so the implementation that I used in the server is actually that it doesn't really care about the timestamps of the inputs. And it treats this connection as if it were a physical connection, regardless of whether it is or not. So it just deals with the inputs in the order in which they arrive, regardless of what their timestamps are. But it only has a single input. So these inputs will be handled in timestamp order, but they will not necessarily be handled in timestamp order relative to the physical actions in this server. Okay. That's a really subtle point, but that subtle point is really brought to the forefront with this impossible consistency program. So here I have two very simple programs that in response to some physical action will produce an output. Okay. And in this case, they're also maintaining a state variable. Okay. And the update to the state variable can occur on the basis of the input. But these, in fact, have a very fundamental problem, right? Which is when a physical action triggers, when is it safe to actually process that physical action? Well, you have to know that you're not going to later receive an input with an earlier timestamp. How can you know that? Well, you can't really, because this physical action could trigger at any time. And in fact, if this physical action triggers, how does this guy know that it can safely advance to that time? Well, it has to know whether it's going to receive an input from the other guy, but the other guy is blocked, not able to process its physical action because it's unsure about what this input is going to be. So there is no choice of this STA parameter that will make this program consistent. In fact, well, that's not quite true. The only choice for STA is to set the STA to forever, which means that when the physical action triggers here, this program will wait forever before handling that physical action and never produce an output. And this is, in fact, the only way using the current decentralized coordinator that you can guarantee consistency. Both updates will remain at their initial balance of 0, and consequently are guaranteed to be consistent. But they will never process any inputs. So it turns out that this problem cannot be solved currently with our decentralized controller. But there's a very simple strategy that we can use that I plan to implement, okay, which is to simply identify this causal chain, the fact that this output will not be triggered for any reason except this physical action. That's information that we have statically in the program. As a consequence, it's possible for this update to send null messages as its local clock advances. So when its local clock hits a certain point, it can send a null message promising not to produce an output before that time. But a key subtlety is that it has to not actually commit a time advance locally. It has to send a null message for a time in the future. So this cannot be done by a reaction in lingua franca. It has to be done by the infrastructure. And it turns out that we have in the centralized coordinator, we have a mechanism that actually handles this situation. But I realized that it actually handles it incorrectly. It does, in fact, advance the logical time at each of the components before sending the null message. And as a consequence, it is still vulnerable to getting safe to process violations. So we actually have a flaw in the centralized coordinator for programs like this one. Okay. But it's a fixable flaw. And that's my plan is to actually implement this fix for both coordinators to send null messages without advancing local time. So I apologize, I've run over a bit, but maybe it's a good time to handle questions. I didn't get any interruptions, which either means I completely lost you all a long time ago, or I was very clear. I hope it was the latter.
No, I think it's really amazing. I think we have seen lots of cases, but also what the difference of the, I would say, use cases are. So for me, it was really great. Thank you so much. But also to see how everything works so fast. That's amazing to see. Thank you so much, Dr. Lee.
My pleasure. So any other comments or questions?
For the null messages you were thinking about, would that be configurable or just some default like null ping loop or something?
It'll have to be configurable because it's, again, going to involve business decisions, right? The frequency with which you send these null messages will affect the availability of the system. And so it will have to be configurable. I'm not sure how to make it configurable. Currently, there is a target parameter that you can use for the centralized coordinator that determines the frequency at which null messages get sent for such a system. So we could just reuse that same target parameter, and then you could choose to send these messages every 10 milliseconds, every 100 milliseconds, or whatever. But they will affect availability. So that if you send the messages infrequently, then these guys it'll put a bound on the time that it takes to respond to a physical action.
Thanks. Follow up. So with these null messages, what is the difference then in the long run between the two coordination models?
So the centralized coordination, it guarantees consistency, or it's supposed to, except for this bug that I only just identified. Which, by the way, I mean, this is one of those kind of bugs that doesn't show up in test cases because we don't have test cases that can reliably generate physical actions. Actually, that's not quite true. In fact, Shulu introduced a test case that generates rapid fire events. So we could probably create a test case that will trigger this bug. I'm going to talk to you, Shulu, about this afterwards because it would be nice to have a test case that causes the centralized coordinator to fail to maintain consistency. But the centralized coordinator is by design supposed to always maintain consistency, which means that as latencies go up, it becomes unavailable. Okay. Because of the Cal theorem, that's unavoidable if you maintain consistency. The decentralized coordinator, interestingly enough, allows you to also maintain strong consistency at the expense of availability using this Chandian-Mishra technique. But more interestingly, it allows you to balance things so that you can achieve a certain amount of availability guarantee in exchange for a certain risk of inconsistency. Okay. And moreover, you can build hybrid systems where you have a portion of the system that is guaranteed to maintain consistency and another portion that is guaranteed to maintain availability. So this is part of what has made me really start to focus on this decentralized coordinator because it's not particularly easy to use. As you can see, there were a lot of subtleties in going through these various design options. So it's not particularly easy to use, but it's incredibly powerful. I mean, and it looks like it can do things that are right up to these fundamental limits, which, of course, no technique will overcome the fundamental limits. But
Edward, but in a way, if you think about those null messages as messages that help coordinate time and progress in a way, then I guess I think you know where I'm going. I mean, I think do we need two coordinators really, or is this just an interim period, or is there something fundamental that says, hey, once we allow this notion of progress of time, which is more subtle perhaps in the decentralized coordinator than in the centralized coordinator, but ignoring the our implementation artifacts, right, which are obviously different here, but are we approaching a limit where really we're talking about the same thing?
well, perhaps. I mean, we can always go to a technique that just discards this notion of time altogether. And in fact, this is what people are doing in practice these days. And then they're discovering the inconsistency problem, and then they're trying to figure out by hand at the application level how to solve the consistency problem. But this is a fundamental trade-off. Okay, because of the Cal theorem, if you want consistency, it's going to cost you. It's going to cost you in availability, and that amount that it costs you is going to be determined by the latency. And so the null messages you can think of as, the absence of null messages, you can think of as having infinite latency or unbounded latency, right? The communication is taking an unbounded amount of time to get to you. And if the latency is unbounded, then either your inconsistency has to become unbounded or your unavailability has to become unbounded. There's no way around it.
So can I do a comment on the last example?
Mm-hmm.
Example. So the alternative of sending null messages is that actually upon receiving a physical event, the update asks his upstream, do you have anything up until this? So basically request a null message from your upstream only to be sent at a time where you actually have something to handle yourself. Have you thought about that?
Yes, in fact, that was your suggestion that we talked about a couple of weeks ago, I think, and I think that would be a very attractive alternative for this. It does increase unavailability, but
Yeah.
well, it gives a different equation, right? Now the unavailability is going to be dependent on a two-way latency versus being dependent on the frequency of null messages. So, um, yeah, let's talk about that offline because that might be a better solution for this case than sending these null messages. That's a very good point.
Is there a variant of that where well, let's say it was update one and update two of in terms of the reactors on your screen, and update one can publish the minimum null that its developer expects?
Yeah, there could. I mean, I think you could definitely have a hybrid of these two techniques. There's another thing you could do actually, which is that if you could just assume that clocks are synchronized, okay, up to some bounded error, and that would tell you how long you needed to wait for an update from this guy. Um, but that's a little bit subtle. It turns out that you can't actually implement that with our existing mechanisms, the safe to advance and the safe to assume absent. It's not quite enough.
Edward, there's another class of distributed systems where, one way that you want to tune the latency parameters is about the percentage of transactions, let's say, that are ending up in the rollback or the failure handling or the inconsistency handling phase.
Mhm.
And that kind of motivates the idea that actually the latency, the STP parameters should be dynamically settable by an agent that is monitoring like latencies. And as the global latencies for your global database are getting worse because of some TikTok, thing, that you don't blindly just still say 30 milliseconds, for example, right? You back off from that and say, look, we can't have 50% of our transactions failing just in this idea that, hey, we want to have fast response times and, make that a bit more dynamic in some way.
Yeah, so that's a very good point, and I think there's a lot of knobs to turn there. But one thing that I think is worth pointing out is that there's predecessors to this Cal theorem paper that define unavailability the way that you just did. It's the percentage of transactions that fail. Okay, that's the way they define it, and it turns out that that leads to an extremely difficult analysis. In fact, there's a paper that shows that the relationship between unavailability defined that way and consistency is an NP-hard problem. So it becomes an intractable problem to find out what the relationship is for a particular design, which is, to me, suggests that that's maybe not the most useful definition of inconsistency from the perspective of analyzing the program. But of course, from the perspective of the business logic of a banking system, for example, that actually might be the definition that you really want. So
If I could push on this earlier point that I was making, I think if you think of the decentralized mechanism as giving you the knobs to take, unavailability and trading it off for consistency and latency, um, isn't on that spectrum, isn't the centralized coordination simply one dot on that spectrum? And
yes,
therefore, the decentralized coordinator is, other than the implementation artifacts, which I would argue in a minute, maybe not as relevant, but other than how you implement them, are we do we think we understand this enough that actually we can make the claim we don't need two different coordination mechanisms, actually?
I think we might be approaching that point. Um, the only caveat that the only thing that gives me some hesitation is that the the only way that I know to maintain perfect consistency with the decentralized coordinator is the Chandy and Misra technique, which requires sending null messages, even in simpler examples than this one. And so there's going to be a cost in network bandwidth and so forth. Maybe we can mitigate that cost with the technique that Arling suggested, which is that instead of sending null messages, you proactively request null messages from upstream guys, and that would reduce the network traffic, but it has a sort of a different operating point on the availability concern. Although, probably if you compare that against the centralized coordinator, I suspect that the latencies would be comparable. So it's
I'd say that the problem is that with cycles, this has some serious problem that
Right.
can be, but it becomes very complicated.
Right. You need fundamentally, I think, to take into account some static structure information about the program. So, for example, when this guy gets asked by a downstream reactor for it, so the time of its earliest possible future output, it should not propagate that request upstream because there is no path from the production of this output to this input. Okay. And so it should use the static structure information that it has, say, okay, I'm only going to produce output in response to a physical input, a physical action. And therefore I can say, well, it's my timestamp, my current physical time is the answer. It should just answer immediately and the loop is broken, right? Similarly, if this was driven by a timer, you would use your information about the period and the next event of that timer. Okay.
Yeah.
So this static structure information is going to be necessary to.
Yeah, but moreover, it's the problem that if actually the output could be driven from the import and there was a delay on the connections between them, then yeah,
Yes.
you have this problem like Christian had in his enclaves that you don't keep these messages keep going around and around.
But if you're using the static structure information, my conjecture is the messages will not keep going around and around unless you have a causality loop in the program. And so the absence of a causality loop may be sufficient. But you do have to use this static structure information. That's the kind of information, by the way, that is present in Lingua Franca programs, but not present in, Hewitt actors or any other coordination mechanism that I know of. You don't have that kind of static structure information about the program. By the way, we have run way over time, so anyone who leaves should feel free to leave. I apologize for that.
One idea to make decentralized coordinator easy to use, I think, is to have the tooling derive a minimum sufficient STA from the assumptions baked into the program, as well as the structure. So I was very intrigued by account 8, because I think that's a very realistic implementation of a business scenario. The one, can you pull up 8? Yeah, so here there's a parameter called true balance period. And also STA is another period, is another parameter.
Yeah.
I feel like what's currently make this hard to use is it's unclear how to set STA and how to set true balance period, such that the STA that's being set here is sufficient, right?
Right.
It'll be very nice if the tooling can take in some assumptions of the program, for example, the execution time of the reactions, the network latency, and the true balance period, and then it generates a minimum viable STA and
Yes.
fill in the program. And I think that would make this much easier to use instead of guessing STA and guessing a true balance period here.
I agree with you. I think there's tremendous opportunities for improved tooling, and I would say it's not what you probably want is also not just to be able to bake in assumptions explicitly, but rather also to be able to instrument a prototype so that you can really see clearly how it's behaving. What is your clock synchronization error? What are your latencies? What are you observing in the field? Right. And how do those impact availability and consistency? Those being able to just have that visibility into what's going on, I think would be tremendous and
Right. Yeah.
really necessary to be able to effectively engineer these systems.
Yes. And I think that also ties back to Irfan's earlier proposal of monitoring these parameters dynamically
Right.
and set the STA based on these monitored values. So eventually the STA could, instead of 30 milliseconds, could just set to auto and it's being monitored live.
Right.
Yeah, and the key thing being that, at least in the way I was thinking about it, right, like even though the unavailability is something that you're monitoring, but you're not reasoning on that. You're still only reasoning on the STA. The program analysis is still on the STA. It's
That's
just that
right.
when you change the STA, you're rerunning the analysis as opposed to trying to do the analysis on the unavailability, which is the prior work that you were referring to, which I'm not familiar with, but in as much as I understood your explanation, I think that the concerns probably won't apply in this case.
That's right. So I think potentially very attractive design here would be one where these offsets are adjusted dynamically as the system is running, and alerts are issued when unavailability exceeds some threshold, right? So if your ATMs are taking 10 minutes to dispense cash, you have a problem that you need to use some human intervention now to try to fix it.
Yeah.
Right. So
With regards to your concern in decentralized coordination of the cost of additional messages, if we continue the assumption of TCP, aren't we basically dealing with keep alive and some amount of sort of somewhat null traffic anyway? And maybe this is a thing where maybe we just piggyback on that. I mean, it's not user visible on the user program side on the receiving end of an edge here in the graph. So it feels like it's extra overhead, but in some way, maybe it's built into the TCP assumption here.
that's a really interesting idea. I had not thought of that, but in fact, that could be a very interesting way to implement this. I mean, it would one way to do it, I guess, would be to just move one level down in the network abstraction layer down to the IP layer and implement a variant of TCP that where the keep alive messages are carrying actually some clock information. That's a very interesting idea. Thanks, Irfan. That's really intriguing.
Again, I'm kind of most welcome, but I'm kind of coming at it from this perspective of, okay, we have two coordinators. And in a way, over time, it feels like we're kind of converging on, well, there's something more fundamental. And I think even calling them coordinators has this artifact of implementation, but actually, really, we're dealing with trying to discover a model of computation in a world where things can fail independently. And
Right.
so in the centralized coordinator, the things that can fail that can really hurt you is the RTI, right? The RTI dies, you're dead. And so you can't really build a real system with that. And so you would have to replicate the RTI. And so now the RTI replication is an interesting protocol that
Mhm.
has to be reasoned through. And then the network in as much as you're using federates with the centralized coordinator, has to be reasoned about and reasoned through in that implementation. All of these are hard problems. We should solve them perhaps, but if solving all those problems doesn't change the model computation, which is what we were going to get with a different implementation that assumes a lack of RTI, then maybe our effort is best spent to say, well, instead of centralized coordinator becoming the production thing that you battle harden using all these layers of protection against failures that you should be protecting against, maybe the effort should go into decentralized coordinator and almost to the point of deprecating the other one, because we don't want to solve the same problems twice if the
Yes.
model of computation is fundamentally overlapping, or not overlapping, completely in consuming the other centralized model of computation, and the decentralized can be done somewhat efficiently, right? I mean, do you see what I'm saying? Like, I kind of feel like, or maybe we're not there yet, but
I think we're approaching that point. That's my sense, and I think that this exercise that I went through with this sequence of examples was tremendously illuminating to me. Right? I mean, I didn't really realize that all of these different methods could be implemented with this decentralized coordinator. I didn't really realize that, and I have to credit Shulu and Jackie actually for opening my eyes to that, because they were the first ones to show that you could actually do this Chandy and Misra technique with the decentralized coordinator, and I had just never thought of doing that. So anyway, I think we are converging potentially to that point. I think the idea that Arling has of, propagating requests upstream, combined with my suggestion that it needs to take into account program structure, might actually be pulling in just a little bit of the logic of the centralized coordinator, and maybe just enough to make the centralized coordinator obsolete. It's quite possible. Okay, well, why don't we end there? And thanks all for sticking around, those of you who are still here. And for the rest of you, well, see you next week. All right.
Thank you very much. Have a nice day. Bye.
Thank you.